Welcome to my video lecture based on electrical machine tool, paper code PCEE 501. Myself, Subram Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Institute of Technology and Sports Complex. Today, my lecture is based on armature reaction of synchronous machine, or rather we can say it is based on two reaction theory. Synchronous machine are basically two types. One is cylindrical rotor synchronous machine and another one salient pole synchronous machine. In cylindrical pole synchronous machine, it is based on uniform air gap, and in salient pole type synchronous machine, it has non-uniform air gap. So, in short, we can say that cylindrical rotor, also called as non-salient pole synchronous machine. Now, analysis of these two machines are basically different, and it will be reflected in their phasor diagram. In cylindrical type machine, air gap is uniform, and if we can remember the phasor diagram of cylindrical in synchronous motor, if this is the flux phi f, then in the 90-degree position it will be the EMF generated, and that will be definitely EF, and it will be only based on cylindrical synchronous machine, and all of these are rotating in this same direction of phi f, because the phi f is created because of IF, the field current. But when the synchronous machine will be loaded, lagging power factor load, then the IA, the armature current, will be like this position. Here it will be IA. Okay. And here phi A will be also in this same direction. This will be also phi A. And these two will decide the resultant flux, and the resultant flux will be here, this position. This is the resultant flux phi f. Okay, so this will be the resultant flux, and due to this resultant flux, the induced EMF will be just 90-degree than this phi r. It will be resultant EMF induced. Okay. Now, this difference of EF and ER, definitely we will tell it as reactance voltage drop. This difference, EF and ER, this difference we will tell it as reactance voltage drop. This will be IA and not IA, it will be XAR. That means it will be IA X AR, reactance voltage drop. Okay. Now let us consider for salient pole structure. This is the rotor construction like this, where the poles are projected outward like this. This is the salient pole structure. Now we will just taking assuming that some fluxes are flowing through this part, and this is the field axis, and definitely the phi f will be along this line. So this is phi f, and not only that, when phi f is dash, EMF will be at a right angle, so definitely it will be here 90 degree from this phi f. Okay, so this is EF, the EMF induced because of phi f. And now we will give some name to this axis, and this line is known as D axis. Okay, and in similar way, this axis is known as Q axis. Now, armature EMF can be anywhere in this space. Let us consider your armature EMF is here, and your armature current is also here like this. This is armature EMF NA, and this is armature current. So this IA is varying depending on the power factor angle. So why not we break up this current into D axis and Q axis? For example, this IA can be thought of phasor sum of these two currents. One is in position of D axis and another will be in Q axis, like that way. We can always find the components of IA in D axis or Q axis. So IA can be combination of ID plus IQ. That means it is combination of current combination of D axis current plus Q axis current. So definitely IF is in this direction, so MD also in this direction and MQ in the direction of Q axis. So in that way we can define the IA currently along the D axis and Q axis. So here is that in case of synchronous machine, when it is about salient pole type construction, the armature flux has some effect on rotor pole, and that is known as armature reaction. And in case of salient pole, as the air gap is non-uniform, definitely the flux in this position where air gap is minimum, and when the rotor is in this position where the air gap is maximum, definitely the amount of flux or armature reaction will be different. Where air gap is more, where air gap is less. Definitely the armature reaction part of the effect of armature flux on field pole will be definitely different. So for cylindrical type synchronous machine, we can tell the total method of armature reaction with help of two reaction theory, and that two reaction theory is based on Q axis and D axis. And here we have shown the phasor diagram at unity power factor. And this is the armature current and this is the EMF induced due to field current. Let us consider this is the field flux, and we know that 90° upward from flux the EMF will be produced. So it is in this position, and armature current will be also in the same axis with field EMF, and this is the resultant flux which is because of these two fluxes, phi A and phi A, and this is the resultant flux, and from the resultant flux with 90° position the resultant EMF will be created, and this is the phasor diagram for unity power factor. Now let us consider the two reaction theory of salient forces. Now, due to the salient force structure, non-uniform air gap is placed inside the synchronous machine. For that reason, two reactants generated in horizontal direction and vertical direction, which I have already shown you here. This is V axis and this is Q axis. One is in horizontal direction, another one is vertical direction. The vertical axis is known as direct axis and horizontal axis is known as quadrature axis. So, this one is known as direct axis and this one is known as quadrature axis. So, we can tell that the reactance which is generated in direct axis, it will be combination of XAR plus leakage reactance XL, and in quadrature axis XQ it will be combination of XAR2 plus XL, where XL is the leakage reactance. The D-axis component of MMF is FA, is denoted by FD, and Q-axis component of FA is FQ. So FD is either magnetizing or demagnetizing, and the component FQ results in cross magnetizing. And if psi is the angle between IA and EF excitation voltage, then FD equals to FA sin psi and FQ equals to FA cos psi. So it is seen that the direct axis flux path involves small air gap and is path of minimal reactance. And FQ is the large air gap and it has maximum reluctance. You can understand from the diagram. In this part, air gap is minimum. That means reluctance will be more or less. Definitely, when the air gap is small, the reluctance will be less, and when the air gap is more, then the reluctance will be also more. That means the reluctance will be maximum when the air gap is large. Since FD has minimum reluctance, so it produces more flux than Q-axis. Let EAD, that is D-axis component of armature reaction voltage, and EAQ is the Q-axis component of armature reaction voltage. Since each armature reaction voltage is directly proportional to stator current and 90° lag behind the stator voltage, so it will be EAD equals to minus JXAD ID and EAQ equals to minus JXAQ ID, where XAD equals to armature reaction reactance in D-axis and XAQ is the armature reaction reactance in Q-axis, where XAQ is lesser than XAD. Since EMF induced by given MMF on D-axis is smaller than Q-axis, that is easily understandable why it is small and why it is total voltage is induced, it will be EF plus EAD plus EAQ. So we can also write that we will put the value of EAD, that is minus JXADID, and we will also put the value of EAQ, that is minus JAQIQ, and we will get the value of total voltage induced. The voltage E dash is equal to the terminal voltage V plus voltage drop in resistance and leakage reactance of armature. So E dash will be V equals to V plus IARA plus JXL IA. The armature current split into two components, IQ and ID, where IQ is the Q-axis component in phase with EF and ID is the T-axis component in lagging EF by 90 degrees. So definitely I have told you in the very first slide that I is armature current, which is combination of ID plus IQ, that is T-axis component of current plus Q-axis component of current. So from here we can write that EF is the induced field EMF, that will be equal to V plus IARA plus JXLIA plus JXADID plus JXAQIQ, and taking common we can write that V plus IARA, we will take common RA and we will get ID plus IQ plus JXL, we will take common and we will get ID plus IQ in bracket plus JXADID plus JXAQIQ. So in that way we are getting the EMF equation, field EMF. So from there we can write that XD equals to XL plus XAD and XQ equals to XL plus AQ. So XD is the direct axis synchronous reactance and XQ is the quadrature axis synchronous reactance. Now EF equals to V plus RA into ID plus RA into IQ plus JXDID plus JXQIQ. So we can write that V plus RAIA plus JXDID plus JXQIQ, where XD is the direct axis synchronous reactance, XQ is the quadrature axis synchronous reactance, and EF equals to V plus RAID plus RAIQ plus JXDID plus JXQIQ, and EF equals to V plus RAIA plus JXDID plus JXQIQ. So with help of this we have drawn this phasor diagram, and we can see that this is the voltage axis V, this one, and with V it will be combined with IARA, this one, then it is combined with JID XD, this one, and again if we divide this part it will be divided into XLIQ and XID ADID, and definitely EF will be combined with all these three, that means it is combination of V plus IARA plus JXDID plus it will be combination of JXQIQ. So this will be combining all these factors, it is EF. So up to this much for armature reaction based on reaction theory, and this is very important part for synchronous machine based on two reaction theory. Now just before finishing the total thing, I want to tell you something more about the phasor diagram for your understanding purpose. Let us consider this is the voltage V and this is the armature current IA. And this is the angle theta. Now we have to add the drop. In case of cylindrical machine, it is very simple, but for salient core machine, it will be different. And armature MMF will be different for salient core synchronous machine. Now I will break up this current into two axes, that is ID and IQ axis. Now as it is generator action, so the EF must be above this one. So EF must be always ahead of V. So, and this is the angle delta. So Q axis will be along EF axis and Q axis is along with this. Now I will draw a line perpendicular to this. And we will say that this is the V axis. Okay. Now if this is the axis, then we can write that armature current, I will take the IA a perpendicular to the axis and this one will be your ID. And this will be parallel with Q axis and this will be your IQ. Now I will add V, I will take J ID XT and this will be parallel to Q axis. And we have neglected RA. And we are considering that RA is 0 here. So in generator mode, EF will be V plus J ID XT plus J IQ XQ and definitely plus IARA. And here if we assume IARA where R is 0, then IARA will be assuming 0. If IQ is along this, then JIQ axis will be along this axis and we will add this one JIQX2. So V plus JIQXT plus JIQXQ will give us the excitation voltage EF. And here the thing we have included RA part also in this diagram, and if we include RA, that means here the IARA part will be adding. As per this diagram we have added IARA, so according to that our IDXD or IQXD has been shifted. So in that way we can draw the phasor diagram of salient pole synchronous machine, and that thing we have explained here. So you can go through the book of Nagrat Kothari in this regard, and also the book of Abhijit Chakraborty is also helpful for understanding the electrical machines, or you can also go through the book of Askar Bhushan for easier understanding. I have taken help of Askar Bhushan for easier understanding, and I will prefer that you must go through that book. And also, as an electrical engineer, you have to also go through the other books like Dhingra, P.S. Dhingra, or books of Koso, or you can also follow the book of Nagrat Kothari. So thank you all, not much more for today. Thank you for listening my lecture.